All right, so we're into quarter 4. Push through, especially you seniors. It's easy to kind of just coast to the remainder of.
Already got acceptance letter.
I know. Well, I'm not so worried about Grant. It's this one I'm worried about. So, I mean, maybe. I'm a little worried about Grant just because he's a senior. But, so yeah, let's just push through. As you can imagine, it doesn't, get easier, and I'm not gonna slow down at all. We're gonna continue to push through, and I know there's play stuff, there's AAU basketball stuff. Oh, not for you. I forgot about that. What do you do with your life?
I might have practice starts today, though, so.
Oh, really?
Are you playing?
I don't know.
You should play. Willie's your coach.
Willie. They start.
It's the first day. It's just
Today is the first
Yeah.
day. I'm definitely not going today.
Probably not.
Well, I haven't even talked to him about cleats or anything.
All
We're
right.
talking about it
I'm
because
not playing sports.
Renee,
I can't play. I don't play sports
What?
anymore.
Corey came over yesterday.
Yeah.
And we were talking about, he was asking if I could
You're gonna play
foot soccer.
Next
He's like,
summer, probably.
well, work out on the basketball team. He was really good soccer player.
If our school's baseball, you're fine.
Midfielder or
Who said
something.
that?
No.
Well, his sister's boyfriend
Yeah.
came to the state.
Anyways. Okay, chapter 15. If we pull open our, you don't have to do this, but just seeing the heading of what chapter 15 is kind of all about, we're talking about. There's a lot of that. It's called acid-base equilibria. So the things that we're going to be doing in this chapter is we're going to be examining things known as buffer solutions. I don't know if we talked a whole lot in regular chemistry about a buffer solution. We talked about its components and what it is. It's essentially a solution that resists a change in pH. That's probably all we talked about when we came to buffer solutions last year. Okay, in this chapter we're going to start doing the equilibrium stuff with it, putting some math behind it, and obviously doing some more stuff. Okay? This is especially important in living systems, which can only survive at a relatively narrow pH range. For example, your blood needs to have a pH of approximately 7.4. But as you guys know, we're constantly changing and eating things and exerting our bodies and creating lactic acid. And if we have lactic acid that's in our bodies that get into our bloodstream, and we need a pH of a specific range, why don't we die? Buffers. Your blood is an amazing buffer solution and can withstand a lot of acid or base that's added to it without having a significant change in pH. And we'll compute that, we'll talk about that. Another really important thing that we will talk about in this chapter is titrations. What essentially a titration is you can use a titration to figure out exactly the concentration of an unknown acid or base by using the opposite of it. So what I mean by this is we know acids and bases neutralize each other, correct? Yeah. Okay? So if we have some unknown acid, we could take a known base and mix it and be able to figure out the concentration of our unknown acid, and vice versa. Okay? So we'll actually, the biggest chunk of this chapter when it comes to math is doing titrations. It's actually basically like 7 different ice tables in one, depending upon how much information I give you. Okay? I don't think it's overly difficult. We've kind of found the shortcut for doing some of this ice table stuff. However, it's all the wrinkles, right? You're going to start throwing wrinkles at you left and right, and you'll have to know what modifications you're going to have to do along the way. Okay? Also, at the end of the last chapter, we talked about adding salts to solutions. For example, One of the ones you guys struggle with at the end of, oops. Okay. I don't know if to be offended by that or happy by that.
Good job.
Heard you beat Becca another 2 times last night.
50-50
She's
is
getting
last
too,
week,
she's getting too easy for you to beat. You're gonna have to step it up and play something a little bit harder. I'm shocked. Are you just so quick that she can't guard you real close and so you hit a 3 on her?
I don't know, usually it's when I'm getting
Because she can't really get super close on you because you're quicker and so you just go right by her?
yeah, I don't know. Because if I
I definitely thought it would have taken you a lot longer to beat her than you did. Anyways, so common ion. If you remember from last chapter, we did stuff like this. We said when this salt is added to a solution, is it going to be acidic, basic, or neutral? Do you remember that? Do you remember that?
no.
Okay. I know you don't remember that because you had trouble. You had trouble with it anyways. Okay? Nope.
Guessing.
No, we-
Let's look at which one's neutral. Which one of these two is neutral?
HCl is a strong acid.
Right.
Okay, so this would be
That's what I
neutral.
was thinking of. Yeah, I was back with that.
So,
Okay.
and NH4 becomes.
And NH4, and you can essentially just kind of memorize this. The anion is the guy that would be the base, cause it to be basic, and the cation is the guy that's going to cause it to be acidic. And it has to do with positive or negative charge. If it has the positive charge, it's likely to give off a proton. If it has a negative charge, it's likely to accept the proton, right? Okay? So then this guy had your positive charge, and so it acted acidic. Okay, or caused the solution to be acidic. What we're going to do in this chapter is we're going to have a salt already in solution and then add an acid or a base to it and see how that affects equilibrium. It's called a common ion. So for example, if I had this salt in solution and I added that's probably not the best example. I'm going to give you an example in a sec. So what a common ion is when you have a solution that gives off an ion that is the same by 2 or more species. So if I had 2 things or 3 things or 4 things in solution that a couple of them gave off the same ion, we would call those ions the common ion. Okay? Well, as you can imagine from an equilibrium standpoint, if you remember, all last chapter we did, when we did our ice table stuff, and we had A plus B equals C, we always said that this, actually,
A plus C goes for the C.
ah, crap. Let's say A goes to form B plus C. We said that this had like 5 molar, and we said both of those were 0, right? We're going to start seeing in this chapter, and we're going to have a common ion here, and so one of these guys or both of those guys won't be 0, which is going to, complicate things a little. Not a ton, but it is one of those little wrinkles I was talking about where it's going to be same idea, but one little shift in thinking. Okay. So before I do this problem. Red is so awful. Alright, let's compare before we actually do a problem with this. I don't know if you have any space for this or not. Let's see. It is?
I believe so. With 1 molar. Wait. I don't know. Yeah, 1 molar NaF solution.
Okay, so what I want to do is, I want to compare when I just have NAF, and what it would be, how it would act differently if I had a salt in there with a common ion. Okay? So the first situation, okay, that guy is only going to have 1 molar HF, and this situation is going to have both 1 molar HF and 1 molar NaF. Now we're going to predict what Le Chatelier's principle is going to do. First off, let's write the equation for both of these. Okay, that is ionic, so what do we know all ionic guys do? Okay, they dissociate completely. So we have that from our salt. And we know that this is a weak acid. It won't completely dissociate, but the equation for the small portion that will dissociate gives me this. Notice what we have. What was that? Okay. What are the F minuses called?
Common ion.
All right. There is our common ion. Okay. Do you remember Le Chatelier's principle? It's what? Anybody?
I remember hearing those words. I don't know the names. It's been a week and a half since we
Yeah.
I know. I'm saying I'm sad that I don't remember it was a week and a half ago.
Le Chatelier's principle. What?
It's
Were you gonna say something that you didn't want to?
That means the cat.
Okay. Le Chatelier's principle is this idea of stress and equilibrium.
That's French for the cat.
Sure.
Le chat is cat. Like that.
How do you know that? How do you know that?
There was a baker at the Chat Noir, it's Black Cat.
Okay. Anyways, so Le Chatelier's principle was predicting how a stress would affect equilibrium. If you remember, Le Chatelier's principle stated that if you cause a stress on equilibrium, it will react in a way that undoes that stress. You remember that? So if we added a reactant, which way would it shift? To the right. If we removed a product, which way would it shift? To the right. And we also talked about, right? If you remove a product, that's the stress. So once undo the removal of product, that's why it will produce more product and shift right. We also talked about temperature effects, and we talked about pressure effects, and all that stuff. Okay? Well, let's see here. Let's say I have this in solution. No, this one in solution, sorry. Let's say I have this one in solution, and then I add this to it. Okay? So what you have then is, if I wanted to do the equilibrium of this acid, because, wait up, I didn't say that right the first time. Let's say I have this in solution first. Okay, so I've completely dissolved that guy, it's broken apart, and then I add the acid to it. Okay? If the salt wasn't there, we could do our normal equilibrium stuff, make an ice table, and figure out how much H plus would be given off. It'd be easy. But if I already have the F minus there, what that's going to be, what that's going to do, it's going to act like a stress. So it's already there. So instead of equilibrium being where it would normally be, is it going to shift it left or right? If we're talking about the equilibrium of this guy,
Left.
it's going to shift it left. Why?
Because there's more product than reactant.
It's like adding a product, right? And if we know if we add a product, it's going to shift in a direction that will undo that, which would be what? Shift which way?
Left.
Left. Okay.
NAF can't shift left because it's completely dissociates.
Sure. Yeah. I mean, that's one way of looking at it.
The other one has to do it.
Yep.
Okay.
And so what ends up happening is this common ion is going to make the equilibrium be a little bit different than what it would be if you had no salt in there to begin with. Okay, and we're going to see the practicality of this when we do this next problem. We're actually going to put some teeth into this one. So way back, I know like 2 weeks ago, it's been such a long time, we did a problem in section 14.5 where we found the equilibrium concentration of H plus when we had this solution, a 1.0 molar HF. I don't know where the M is there, but okay. We found what the concentration was. It was this. Okay, and we found out what the percent dissociation was. It's the 5% test. Okay, now it wants us to do the exact same thing, except for we have some salt in there as well. Kind of the idea that we just talked about in theory a second ago. We're going to do the math with it. And the very first thing we should figure out is what is important. We know that we have HF, correct? Okay? And that's going to be the dominant of that reaction, right? Because it's not going to dissociate very much, correct?
Yeah.
Okay? Then we have NaF, that's ionic, so what will it do? We'll have a lot of that, we'll have a lot of that, and we'll have some H2O. Okay? Now let's figure out what are things that are important here. This is,
We don't have any H plus at all.
well, we will, but it's not going to be the main thing for that reaction. What's significant about this? It would produce a strong base, which means this ion is
A strong base.
Weak acid conjugate.
true.
It dissociates.
It wouldn't form.
Thank you. It has its neutral properties.
No, we're right.
You guys aren't saying wrong.
Yeah,
thing.
You're all doing what I usually do. It's a correct answer technically, but not the one he's looking for.
Well, yeah. I'm looking for the correct answer to this situation.
And then F would produce a weak acid.
Right, so before we do that, this is also going to be extremely weak. So what is going to be important for this particular problem is that this and this are important species. When you're doing these salt problems, you have to be able to identify the ion that's important. Now, usually, it will be a common ion that would be given off from either an acid or a base. Does that make sense? Okay, so we're going to try to figure out the H plus concentration and dissociation of HF. Our reaction would look like this. Okay, we could set up an ice table. Now normally we would write the equilibrium expression first and all that stuff, correct? Okay, but we've done that so much, I'm going to kind of just skip it. What was that?
And then we get docked points
What?
on the test for not showing all the work. I don't know.
That. Okay? Now I have 1 molar of both. Okay? Initially, I should have 1 of this. This is already in solution and has been dissociated. So what? And I technically have none of this before I've started any reacting of my acid. Okay, the change. I still have 0 of this, so it's likely that even though my equilibrium lies far left, I still have to proceed to the right to get there.
Okay.
Does that make sense, everybody? I mean, this is going to be even further left than a regular weak acid problem because of the addition of a common ion, but it's still, because I have none of this, I'm still going to go at least a little bit to the right. Which that tells me that I'm going to be reacting that, correct? And I'm going to be producing this. Very little of it, but still going to be producing it to get to equilibrium. Questions so far? Anybody? What would be next? Okay, put it into the equilibrium expression. What are we going to do? Here. Our Ka value. And then products over reactants. We got X. One plus X and 1 minus X. Now here's a situation where we have an initial concentration with an X not only on bottom but also on top. So what we can do in this situation, before you get too far ahead, Grant, we can remove the X in both. What I mean here is, if we say this X is so small that it isn't going to affect this one, why can't we say this X is so small and it isn't going to affect that one? Does that make sense, everybody?
Yeah.
So to make the math easier, I can remove that X as well as that X.
So it's just that was my two.
So in this context, your X is going to be just your Ka. Okay? So this would answer the first part of your question, which is that, correct? Because X is H plus concentration in the context of this problem. Right? Everybody get on that? Okay? Then it wants a percent dissociation, which is essentially the what?
The 5%.
The 5% test, which is our X. Quick refresher here. Over our initial concentration of my acid, which is 1 times 100, should give us a really low percent dissociation. And it does. So let's compare the dissociation with the common ion in it with the dissociation without the common ion. When we did this in theory, before we did the math, what did we say was going to happen? Which way did we say it was going to shift? What? Left. From a dissociation standpoint, did it shift left? What? It did, right? Before I added the common ion, this is how much dissociated. After I added the common ion, it dissociated less, which means it shifted left from equilibrium from our original standpoint, our original situation. Okay? That should make sense. Another thing here that this becomes a pretty important connecting piece that I would like to share with you. You guys remember when we did polyprotic acids? Okay, so for example, we did this guy, and if you remember, the polyprotic of that guy had 3 Kas, correct?
Yeah.
And we said which Ka was the strongest?
The first one.
The first one. And part of the reason why the first one is the strongest, yes, it has no charge, and we said the second one and the third one have a stronger negative charge, which makes it less likely to dissociate, correct? But wouldn't the first step produce a common ion that's there in the second step? Does that make sense, everybody? So for example, when I do the second dissociation of this, don't I already have some of that present from the first dissociation? Wouldn't that act as a common ion, which would force the equilibrium to be further left for this guy, making it a lot weaker? And then the third step as well. So not only you got the fact that it has negatively charged now, and it's not as likely to give off a proton, but you're adding a common ion, which is going to force the equilibrium to shift left. Does that make sense? All right. We are.
Is the percent, so if the percent dissociation ends up being more, it would shift right?
Technically, but it won't for a common ion.
Common ion always make it shift left, make it weaker.
The only way it wouldn't if for some reason you had a common ion that was a reactant, but we won't come across it. I don't know if that's just not possible, or we just don't do it, or just not likely. Okay? All right, 6 minutes. Wow. Probably get your, what, one problem done?
Yeah, it's the definition of common
Oh, are you serious?
ion. That's not every time.
Wow. Wow, Mr. Kramer.
Thank you, Mr. Kramer, for letting everyone